then. So we're going to look at trends in group 7. So we've already had that. As we go down the group, Timmy, what's that trend that we had going down?
Even more electron shells.
No, just give me the trend first.
Oxidizing strength decrease.
Oxidizing strength decreases. That's grand. And the reason for that, Timmy?
Because the more electron shells.
More electron shells, so more
shielding.
More shielding.
And so that means there's a weaker attraction between the nucleus and the electron from other atoms.
Yeah, so a weaker attraction between the nucleus and the electrons that fluorine is trying to grab hold of, whatever it's reacting with. Okay, why would we expect oxidizing strength and electronegativity to have the same trend? Why would we expect oxidizing strength and electronegativity to have the same trend? What do you think, Abdullah?
They both depend on the ability of the atom or the power of an atom to attract the electrons.
Electrons, yeah, that's a perfect answer. They both depend on the ability or the power of an atom to attract electrons to itself. Okay, great. The other trend I want to look at, well, electronegativity is in your topic booklet there on page 8. The other trend that I wanted to look at was the boiling point. How would we expect the boiling point to change as we go down the group? And more importantly, why? How would we expect the... No, I'm going to let people think about it. I mean, the answer's in the topic booklet, but try not to look at the answer. If you've already looked at the answer, then you already know the answer. But how would we expect the boiling point to change as we go down the group, and why? I'll just leave you with that for 2 minutes. So, gents, Adam, could you go for it, thanks, without reading it from the topic booklet? What's the trend?
The molecules increase in size.
So, what's the trend first?
The boiling point increases as you go down the group.
Let's just put it over here. Because
the atoms increase in size, or molecules increase.
Yeah, molecules. I mean, yes, the atoms increase in size, but molecules. What's the? It's not the size of the molecule so much as the. Not radius, no.
Is it the nucleus?
It's not the nucleus. What is it that's gonna? What's the force that's gonna increase our boiling point?
Like the intermolecular forces.
Yeah, which one? Yeah, Van der Waals. Okay, so what is it that causes Van der Waals forces to arise?
Is it just the electrons?
Yeah, it's the electrons, right. So more electrons is the significant factor. Obviously, bigger molecules have more electrons in it, but it's not because they're big that they have stronger Van der Waals forces. It's the fact that they have more electrons. Okay, so more electrons, so stronger Van der Waals forces. Okay, great. We can keep going, can't we? Which require more energy to break or you don't really break a force, you overcome it, don't you? Okay, fine. So, yeah, if we look in the topic booklet there we've got, it's quite a significant difference, minus 188 for fluorine and then minus 35 for chlorine, 58.8 for bromine and 184 for iodine. Yes, so it's a significant difference because the molecules are bigger. Yes?
Is that the boiling point or oxidising strength?
That's boiling point. Those, sorry. Oxidizing strength numbers we will look at in the next redox topic, which will be in year 13.
So, will it be the opposite direction for the halides?
Strange question to ask. That's exactly what we're doing next. Okay. Okay. So the first question we need to know is, how does boiling point change as we go down the hydrogen halides? So we're looking at substances that are by and large gas at room temperature. So the boiling points are going to be fairly low, and we're going to dig into this for a minute because it's not a straightforward and simple trend. There's quite a lot going on. So I'm just going to leave you for a minute to think about what the trend might be, and we'll have some discussion about that and see if we can get in the right direction. Okay. Let's see if we can make any headway into this. So everybody's come up with the same observation about HF, which is okay. So hydrogen bonding is a special intermolecular force. Could anyone describe how a hydrogen bond arises? Do you want to make a start?
Is it the bond between the hydrogen in one molecule and the fluorine atom in another molecule?
Oh, you're so close. What about the fluorine atom?
It has a lone pair.
A lone pair, exactly right. Yes, so fluorine's got several lone pairs, but because of a big difference in electronegativity, you can see here fluorine's got an electronegativity of 4, hydrogen is 2.2. So big difference in electronegativity means a very polarized molecule. That's the condition for hydrogen bonding to occur. You've got to get a big difference in electronegativity. And then the interaction between the H delta plus and the lone pair on the F causes the hydrogen bond. Yes?
I was going to ask, would it not be permanent dipole-dipole interaction?
Right, we'll come to that. So strongest intermolecular force, intermolecular IMF. So yes. So in answer to your question, yes. If you've got hydrogen bonding, you of course have a polar molecule, so you would get some dipole-dipole or permanent dipole-dipole forces between molecules as well. You also get van der Waals forces. Van der Waals forces form for every single molecule that exists, not just the ones that don't have dipole-dipole and hydrogen bonding. All molecules have van der Waals forces. That's an important point. Right.
So, was that INF?
Intermolecular force. Okay, so what does the electronegativity data tell us?
Decreases as you go.
So it was decreased. Oh yeah, because you know the first one, the oxidation
Someone at the back there? Jamie? Tell us what strikes you about the electronegativity data as applied to...
As you go down through the electronegativity, gets closer to halogen.
Okay, so the all-important thing here, for the polarity of a molecule, where X is one of the halogens, is the difference in electronegativity that matters. So HF has a very big difference in electronegativity, so it's a very polar molecule. HI has almost no difference in polarity, so it's not very polar at all. So as we go down the group, the difference in electronegativity decreases. Difference in electronegativity decreases, so Hi is a weaker dipole than HCl. Does that make sense so far?
Yeah.
So, based on that, what would we expect the graph of this data to look like? Running out of board space over this side.
I think Ollie's
Don't need that, do we?
No, genuinely use what you're saying.
Graph HF, HCl, HBr, HI. Somebody want to take a chance? Okay, for it.
He's not talking about this.
Okay.
Can I describe it?
Yes, you can describe it, yes. Might not want to be on camera anyway.
Does it start near the top?
Starts near the top, so this is boiling point, yeah?
Then it steeps down to HCl.
Yeah, and then,
And then it gradually decreases to
Okay.
HBr and HI.
like that?
Yeah.
Hmm.
They might be.
Okay,
Oh.
right, so the information about electronegativity implies that HI is going to be the weakest dipole, so it's going to have the least dipole-dipole forces, so we'd expect it to have the lowest boiling point. But that's not what we see. So what is this data telling us? There's nothing wrong, by the way, with what Ollie has done. He's made a correct inference from a correct idea, but the data goes in the other direction. So what is the data telling us? Can just let other people have a think about that, because it's quite an important question. Okay, so
Joe's coming up with some good suggestions.
that's right. Throw Joe under a bus. Why don't you?
He was actually making a good point.
No, actually, it wasn't.
He was genuinely making a good point. Do you want to share with us, Joe?
I thought like bromine and iodine have more electrons,
Yes,
so bigger molecules,
yes,
so be more van der Waals
that's
forces.
exactly right. Yeah. So what we've got is two things that oppose each other. As we go down the group, yes, the electronegativity difference decreases, and yes, they're going to be weaker dipoles as we go down. But they're also larger molecules. And as we found out with the halogens, F2, Cl2, Br2 and I2, the increase in boiling point is not insignificant, is it? We've gone from minus 188 to 184. That's a big difference just because iodine is a bigger molecule than F2. So larger molecules, stronger van der Waals forces is going to increase boiling point. So the data is telling us that of those two factors, the van der Waals forces increase must be the more significant factor.
Right. Over what other factor?
The weaker dipole. So the fact that HI has got the weakest dipole doesn't really matter because it's such a much larger molecule, it's got a much higher boiling point as a result of van der Waals. As I said, all molecules have van der Waals forces. Doesn't matter if they've got dipole or hydrogen as well, all molecules have van der Waals. So although HCl has a stronger dipole and therefore stronger dipole forces, actually it's the stronger van der Waals forces of HBr and HI that are the significant factor. So the increase in van der Waals forces is a more significant factor. In determining boiling point. And the dipole forces. Does that make sense? It's very hard, this, very complicated. Notice it's exactly the same for water. So this water, of course, is kind of oxygen hydride, if you want to call it that, H2O, and H2S is sulfur hydride or hydrogen sulfide, and hydrogen selenide and hydrogen telluride. As we're going down group 6, those are the elements we get, and we get exactly the same shape. So H2O has hydrogen bonding, which gives it a disproportionately high boiling point, 100 degrees, of course, for water. And then H2S is right down here, around about -50, -60. And then we get an increase, steady increase, exactly in line with HBr and HI for H2SE and H2TE because of an increase in van der Waals forces, because the molecules are getting bigger.
So, as we go down the halides, boiling point increases. But does it decrease?
What?
You know that one?
As we go down the hydrogen halides, well, no, HF is the highest because of hydrogen bonding. Then, so we get a sort of break there, but then we get a steady increase. Okay, so you can't really say increases or decreases. That either of those words is wrong.
What for the boiling point?
Yes.
Is that why you have the question mark?
Yes. HF is the highest because of hydrogen bonding.
Yeah.
And then HCl, HBr, and HI increase in line with van der Waals forces.
If we get a question about the trend of the hydrogen light, should we say about it decreases then increases?
I wouldn't say that. I would just say HF is highest because of hydrogen bonding, and then HCl and HBr and HI increase because of the increase in van der Waals forces. So the question you could get on this would consist of this data and the electronegativity data, asking you to explain what's going on. It will be 6 marks, and it will be a very evil question.
Yeah.
It'll be very hard to come up with all of this in the exam. Okay, that's all I wanted to do on that. Can you complete exercise 3, questions 1, 2? That should take us up to the end.